Screen is, thank you. The first one up on my screen is Brett Bode from NCSA. Brett, introduce yourself and tell us what you think.
All right. Again, I'm Brett Bodie from NCSA. I've been here about 18 years now. Came to NCSA to work on the Blue Waters project, which, if you might recall, was the Track One system before Frontera. So it was a very large system, which resulted in a lot of infrastructure being built, including our data center that we're now using. I was involved after the initial design, but while the building was being built for our compute facility, and have been involved with a number of projects, including Blue Waters. Since then, I'm currently Deputy Project Director on Delta and Delta AI systems, which are NSF-funded Category 1 systems that we operate for the NSF and the National Research Community. I've been involved with other projects related to data center management, and attended some of the European data center uh, uh, meetings on how to improve efficiency and that sort of thing. So we are very interested in improving our efficiency, though, as many of you know, improving efficiency often takes money to save money, and that's not always easy to come by.
Cool. Thanks, Brett. And Brian from San Diego Supercomputing Center. Brian.
Yeah. Hi, everyone. I'm Brian Balderston. I've worked at SDSC for about 15 years, and my role there is the Director of Infrastructure and Data Centers. Um, we have a 19,000 square foot facility, about 3.5 megawatts, and for um, the last 5 years, actually 6 years, I've been kind of directing and overseeing that facility. And then before that, for a few years, um, kind of providing some strategic oversight, but not necessarily um, overseeing the facility. Um, my team is in our research data services division at SDSC. And what we do is kind of everything around HPC. So we have the data center, we have networking and storage and custom clusters and virtual private clouds, research support, data management. We have uh, several people that work on data-driven initiatives and grants, and, and our division has the data center. And so I've been working on not necessarily like the best and the most efficient facility, but we've been working on kind of incrementally improving our efficiency over the last decade. And I have a few things to talk about what we've done and what we've looked at. But yeah, that's my overview, Chuck.
Cool. Thank you, Brian. To get us started here, the questions we have right now currently are all circled around basically the impact of AI is having on our data centers and how that's impacting some of the green and environmentally friendly computing concerns we may have. So I'll start the first one. I'll point this one to Brett first is how do you address the ethical dilemmas that AI might bring when it comes to power and water consumption? What's some of the concerns we have there, and how would you propose we address them?
So we are looking at that. Our data center was designed, probably not the most up-to-date design today, but it was designed and built, around 2010, 2012, and it did include direct water cooling as a key design point. So we do have capability to do direct water cooling throughout the facility. Some of that wasn't built out as much as it should have been, and we're trying to address that in projects we're doing today. So, but we are well positioned to deploy water cooled or some sort of water assisted cooling in our facility. We also have connections either to the campus chilled water system, which uses mechanically chilled water, or we have on-site evaporative cooling towers that we can use um, uh, most of the year now. With Blue Waters, our required inlet temperature was too low to use them full year round, but they could be used around a little more than half the year. Today, we've been able to increase that, and the newer systems that use direct-to-chip cooling allow larger inlet or higher inlet temperatures that help us with that. Water usage is a concern, is of course um, not so much because of how much we're actually using, but how much, the press that's coming out many places, including here in Illinois, about new data centers that are, of course, our data center is 24 megawatts of built out capacity, though we're not using anywhere near that much today. But that's, an order of magnitude or, even more lower than smaller than the capacity of these large data centers that are going in commercially. So their corresponding water usage is substantial, since most of these facilities use evaporative water cooling in some fashion as the go-to solution for getting rid of the heat that, of course, the electricity is generating throughout these systems. So we are working with our campus here as well as our state water survey folks, the Prairie Research Institute here, to kind of study that and look at which areas are sensitive to additional drawdown of water supplies and that sort of thing, and which areas are not within the state. And of course, there are many other parts of the world that are much more sensitive to water supply issues than what we are here in the Midwest, actually. So it is a major concern, and we are continuing to look at alternatives to uh, water cooling and other sorts of things that don't consume as much water. But as I started to say earlier, those all have costs involved, and it's hard to justify those in the current climate, at least for us. But they are, dry coolers and other things that are do make sense in other contexts. We have also looked at waste heat recovery and using that in other parts of campus, which also improves the overall greenness of the program. For us at the moment, we haven't been able to implement that because um, the heat that we generate is too low grade to be efficiently used for heating in other parts of the campus there. But there are other solutions that, again, require initial capital expenditures that could make that more effective. So those are also things that we are considering and would implement if we had the right financial environment.
Yeah, I have a follow-up question. I'm going to wait till after Brian has an opportunity to chime in, though. So, Brian?
Yeah, we're running into a lot of these same issues with trying to get campus to pursue efficiency projects, but them being pretty expensive and not really getting so much off the ground. We also brought liquid cooling back to the facility in 2020 um, for our Expanse supercomputer, and in the last 5 years have done a number of upgrades. We did put in an evaporative cooling tower on our site, and that was an efficiency measure because we can, with our weather, run that like 10 and a half months without modifying our inlet temperature, which is unfortunately lower than it should be because the way that our facility was originally designed was we had our air handlers on this kind of secondary loop, closed loop, and that's what we tapped into to do the direct liquid to chip. And so if we tease those apart, we could
Yeah.
elevate the inlet temperatures on the DLC, and that's one of those projects that we would love to pursue, but we don't really have the capital to do that right now. But we've studied that, and that's something that we would really like to increase our delta T, increase our inlet temperatures, and take a full advantage of the evaporative cooling tower. Um, on efficiencies, one of the things that we're kind of stepping into recently is looking at exploring grid-aware software and tying that directly into Slurm on some of our computers with the local utility and some third-party software vendors, so that in the event of like a California load shed, instead of just completely like preempting and curtailing everything, we would have our scheduler be kind of aware enough of what's happening to make smarter decisions on um, preempting any jobs that it might have to. Um, in the past couple of years, we've had to during a massive event where we're getting pinged from the utility to do everything we can to shed load. It's kind of just been a try to turn everything off type of situation. And so looking at ways that we can um, explore actually integrating our HPC systems in with grid aware technologies. That's something that we're kind of just getting off the ground early this year. Um, and we're working with our Center for Energy Storage on campus, and which is a research unit on campus all about energy, and San Diego Gas and Electric. And yeah, that's that. I don't know where that will go, but it's kind of a maybe an interesting way that we can um, help the kind of the California energy situation with all of these data centers popping up, but also power being so kind of expensive and difficult to get to the load pockets in California.
So one follow-up question I have for both of you, and I don't care who takes it first, is both of your centers were built, like you said, decades ago, so to speak, and you're trying to retrofit them to meet the demands and needs of the current like the current um, aspirations to get things as eco-friendly as possible in multiple angles. What would you suggest, or what would be the first way if you were running a data center, say that's maybe half or smaller scale, to address those concerns? How would you approach it first? I heard some of it was the grid aware stuff, but what would be some of the things you would suggest to folks here that have those problems of trying to attempt to deal with it?
Well, I guess I would say that some sort of direct liquid cooling, if it's at all practical in the data center, some you may not have a source anywhere close and it just may not be practical, but if it's practical to pull that into the data center, that can be a pretty significant win, especially as we're moving forward with next generation GPUs that are getting even more heat or power dense, and therefore the air cooled versions of Blackwell servers have absolutely massive heat sinks in them, and they're pushing 1,000, 1,400 watts per GPU. Next generation is probably going to either have to throttle the processor a lot, or they're going to require liquid cooling to operate those in a in their flat out environment. So that's an investment that you may need to make anyway, but it's also an efficiency investment because it's um, quite a bit more efficient to pull the heat off these chips with direct water cooling than it is to have to air cool them and then pull the heat out out of the room some other way. And indeed, we have a variety of water cooling and air cooled systems in our data center at the moment. They range from systems that are air cooled within a plenum that has a heat exchanger inside, rear doors on air cooled equipment. We have direct to chip systems that are typical servers with direct to chip cooling for the processors and GPUs. Those work, you get about 70% of the heat or so cooled to the chip that way. And then we have systems that are 100% water cooled in the center as well with the Cray EX platforms. And those are the most power dense racks. The racks we're using there are their baby racks, which are only 135 kilowatts per rack. But they have zero fans. So we're getting a very dense environment with no noise, no extra power usage by fans and other cooling equipment, just CDUs that pump water through the system there. And that maintains a better temperature on the processors as well. You don't have many thermal excursions. So that's a big one if you can get direct water cooling in the center and then make use of some sort of evaporative or dry cooling if that's appropriate, on-site cooling of that externally so that you have you're just pumping water in and out of the data center and not having to pay for the crawl fans and everything else to move that heat.
Brian, do you have anything to add to that, or?
Yeah, when I we have one of the 135 kW EX series crays, 100% liquid cooled, no fans. And when I give a tour, I you can actually talk next to this, and I say like, when I look at this from a facility perspective, and this is where like the metric like PUE, in my opinion, could get like reshaped a little bit, or you can rethink about it. This is like 135 kW. Maybe there's a little bit of loss, but it's basically all doing compute science research. We're actually using that. And if I walk over here, like, okay, here's 5 racks that's doing 135 kW of air cooled. I mean, I don't know where to swag it at, but I'll say 30 kW is just little plastic fans pushing air around. And, that's like this like parasitic load that isn't really factored into like, your efficiency metrics too much. Not at least not the kind of the standard PUE that we've the data centers use because it's inside the chassis. Um, but it's some real fraction of the load is just these little fans. And to me, that just the efficiency of water versus air by volume, and the efficiency of the pumps versus the fans, it is it's been a really good investment. And I know in the abstract there was a mention about metrics. That is something that we're um, a little bit we've had so many discussions on this, but we haven't come to the right way to really display our metrics on how to um, quantify, or like what we want to quantify and how we want to present the kind of efficiency gain of a 100% liquid cooled versus maybe that 70% or a completely air cooled system. But it is something that we're looking into. So I don't have like a great. I'd be happy to hear if other people have a good metric for this. But we've looked into like the water usage effectiveness. We've looked into kind of refactoring PUE with this in mind. And so that's kind of a current project that we're working on, is trying to find the right metric for us at least.
Cool.
I guess I would also offer that these direct to chip and other 100% water cooled solutions also open the door to other efficiencies and reuse of heat and that kind of thing, because they raise the bar on where the temperatures are at. So, you can do inlet temperatures that are as much as 90 degrees Fahrenheit, and therefore you get heat out that's coming out of the water temperatures are a little over 100 degrees or more, which starts to get more interesting to recover heat to do other things with. Whereas air-cooled solutions are typically, you're probably only producing water temperatures that are like 70 degrees, or if that, because you're having to keep the room quite cool to do that air cooling. So it really can open the door. In Europe, where power is more expensive, they would employ uh, uh, thermal pumps to boost that temperature up from 100 degrees, and then transfer it to district heating systems and things like that. So again, it takes a little money to do the heat pump, but it's still a way to recover that heat and put it into other places that would use it for heating buildings and things like that. So that's much more efficient. Obviously, the warmer your outlet temperature is, the easier it is to recover that heat and make use of it elsewhere.
Very good. Scott, would you like to comment on what you put in the chat there about Alberta?
Yeah, briefly. I mean, one of the benefits of being at 53 degrees north latitude is it's minus 17 degrees centigrade right now outside my office window. So, all I'd have to do is break the window to immediately cool everything. But, in the summer, it's 30 degrees. Oh, sorry, 84 degrees. So, uh, we have a wide variety of temperatures, but a lot of the time you can just dump the heat outside. But in the data centers that they had been running HPC equipment in, they were recovering the heat and using that for heating up the same building because basically the data centers on the first floor and then they have offices on the next 6 floors and they heat the building mostly through that. But they've got this giant, it's a looks like a water tank that's sitting over by one of the parking lots and it's just chilled water.
Hmm.
And that's that final 5,000 tons. Uh, and there's always this scar in the ice of the North Saskatchewan River that's open water, even in January and February, where they can swap the heat from their chilled water loops of the campus down into the river, and they've got free cold that they can then store, and that's been useful in the operation of high performance equipment. And then, of course, the chilled water loop is how they air condition campus and also chill, data centers, of which they've got three. So,
Thanks, Scott. Um, Pamela, you had a question in the document. I was going to give you an opportunity to pose it now. All right, so go ahead.
Oh, this is a little bit more of a tangent, but we had an AI summit last week, and Jamie Garcia from IBM Research was pointing to a lot of these issues and saying that's why they're investing in quantum as a way to tackle this energy and heat, water. And I'm just curious if that's something that any of your centers have started talking about, maybe shifting some more focus to that area, or if it's still like we just have to wrestle with current demands and be aspirational later.
So, Brett, do you want to talk about the quantum computing here, or do you want me to do it?
Well, quantum is a different beast entirely, right? I mean, it has different requirements. Potentially can coexist in a data center, though I think they prefer to have it in a low vibration environment, so that may or may not be compatible with. Certainly, air-cooled equipment tends to generate a little bit of noise, and our data center happens to be only a block away from a major freight rail line too, so that also could pose issues with a quantum computer. But apart from that, they tend not to be terribly power hungry. They're much more power efficient than certainly our AI systems are. So we are exploring that. At the moment, it looks like a quantum computer will probably have a classical computer sitting alongside of it, helping manage it and operate it. So how that works and how far away they can be and still be effective in that process is something that we're exploring with at least one project, and I think we're probably looking at a couple more. Um, but yeah, it's an interesting technology that isn't quite ready for being deployed on site, I think, here yet in a real production sense, but some exploratory systems are being looked at.
Cool,
Thanks. That's exactly what I was curious about.
cool. All right, some other questions. Does anybody have any questions to the audience? All right, I'll throw another one from our list here. Okay, well, I'm just going through one list. So, just out of curiosity, what metrics are you guys using to capture and use to formulate your strategy and policy with respect to green computing at your particular facilities? Brian, you want to go this time?
Yeah, so we have always had like a all of the data that would go into the power usage effectiveness, just dumping into a graph database, and we can like um, see how the improvements that we do kind of affects this over time. And we actually had someone at NCSA come out and help us kind of build and make sure that we had one of your engineers, I forget their name, this was like 7 years ago, kind of make sure we had all of the right data kind of feeding this. And that was kind of great for a while. We replaced some air-cooled HPC with liquid cooled. We saw like the PUE that we can actually advertise for these facilities drop from like 1.35 to 1.26, and we see it fluttering. Um, not that that's a really accurate representation, to take a point in time measurement, but and so that's kind of the typical one that most data centers have used and what we've used. Um, but I think over just the last year, we've felt like that doesn't really um, that doesn't really show the whole picture. And if we're kind of layering on this like power multiplier to a customer that's buying an air-cooled circuit on 208, where I have to transform the power another time and cool it inefficiently, and I'm delivering that same power factor to a customer that may be able to exist on in an ORV3 cabinet with uh, you know DC shelves being powered by our 480 bus with kind of a shared end of row cooling distribution unit. Like that's so much more efficient from the facility standpoint for us to deliver this. And so one of the things that I'm wrestling with a little bit is what is like, I mentioned this before, like what is the right metric for us to um, kind of to show how much more efficient that customer is that is leveraging the centralized infrastructure investments that we've made versus the kind of just dropping in, some system with a bunch of GPUs in it, air cooled, and that takes more strain on the facility. So I don't have a great like um, solution of what we've done with metrics. It's something that we're exploring, and but we know that there is a need to kind of figure out what is the best way that we can kind of show the efficiency of a system like that, like the Cray that Brett mentioned, versus um, similar compute power, but just in your standard chassis.
That's a tough, yeah. Metrics are a tough one. As one of my colleagues like to point out, you tend to you pick your metrics based on what actions you wish to encourage people to follow, and that's not always obvious exactly what that might be. Um, we're struggling to redefine our cost recovery mechanism for our facility. We, I don't know, perhaps different than many sites. Our center, our National Petascale Compute Facility, was built. It's owned by campus, but it's treated as an off-campus building. So we get charged for everything there. It's like a departmental facility where we pay power, we pay for light bulbs, we pay for janitors, we pay for everything that would normally be in the overhead rate of the university. In exchange, we do get an off-site overhead rate that's considerably lower than the main one. But we have to pass those costs on then to the occupants of the facility. And how do we divide up those costs? We had been using just a floor space based method, but that's not necessarily encouraging the right things these days, where you can now use all the power in the building without using anywhere near all the floor space. So it's not necessarily the most fair thing. So as Brian mentioned, the cost of a 208 volt circuit is higher for us than a 480 volt circuit, because we've got 22 480 volt transformers downstairs, and anything that's lower than that, we have to have a smaller way to, another transformer to step it down. So I agree. That's something we're trying to figure out, is how do we charge appropriately for the power capacity that systems require. and their impact on the cooling of the facility as well. So whether they're direct water cooled or whether they require lots of air cooling. 'Cause, I think I mentioned we have 24 megawatt power capacity. Well, we have 2 megawatts of air cooling capacity. So you can do the math there. We cannot have all that much air cooled equipment directly in the facility. There has to be some sort of water assist for the bulk of it. So those are, yeah, excellent points. That you need to think about the metrics to get people to optimize their solutions to what you want to see in the facility. Because I mean, it's certainly cheaper to drop an air-cooled server into an air-cooled rack at 208 volts if you're not making them pay anything extra. Doing water cooling with a rear door or with even DLC, it requires additional CDUs and things like that that have an upfront capital cost. And it's uh, not always easy to get people to see beyond that.
I agree with that. Let's see here. Anybody have any questions coming out of the group here that before I start pulling another prompt question out?
I have a quick question on the PUE, right? Like Brian, you mentioned you've dropped your PUE from 1.35 to 1.26. Uh, so how did you leverage, like what, I mean, did you actually leverage that? Yeah, this we have achieved better efficiency now in getting additional funding maybe, or like how did you use that information?
Yeah, I mean I use that to deliver kind of an estimate of savings to the campus to try to get them to help fund additional efficiency capital projects like this is how we got our the evaporative cooling tower on our site. And so we have kind of a handful of other capital improvements that we'd like to pursue. I kind of talked about the kind of teasing apart the air handling units and the DLC. These things are like $1 million, if not a couple $1 million just to do that efficiency project. And so it's just that calculation I've used to just give it back to campus and say, our facility is, well, right now is using like 3.5 megawatts. We dropped the efficiency. Like this is what the savings is, and power's not cheap in San Diego either. And so they can be some pretty big numbers. And the payback period on our cooling tower, I think the campus told me was like 11 months. And we can use it like almost 11 months out of the year. So it's like that was pretty, a pretty good project that we had been pushing for since before I even got involved in the facility. We had been pushing for economizer on the water side. And so that's how I've, I guess, leveraged that metric internally, is just to show like that these capital improvements do have a meaningful impact on the financials.
I completely second that. We do much the same. We have the same challenges. Perhaps I'm not sure exactly how you're paying for your power, but one of the implications of the way we're doing things is, we charge grants and other things for power usage often, which means that, but you can't usually charge them directly, at least for improvements for efficiency that are capital based for the facility. So you end up asking for the money for the capital improvement from campus, which is taking it out of a pocket that's different from the one that's paying for the power, which doesn't always, they don't always see see why that should work. So that's another thing we're trying to figure out, is how to work that into our rates such that we can effectively self-fund those through the recovery cost recovery mechanism for the facility. But it's a challenge. As Brian said, these things, you don't do much for under $1 million. these days. And the water stuff is actually the cheaper stuff to do. And you can actually get people to do it in a reasonable amount of time. If you want to do power stuff, be prepared to wait. Transformers take forever. So, as do much of the other components. So, we're changing from, the old style of building out power through um, individual power drops from uh, uh, breaker bays and things like that, breaker boxes, into overhead bus bars, which have, movable power taps that can be changed at any time live without having to take the bus bar down, or things like that, which are, I think, in the long run, going to be a real nice advantage. And there's a lot less rip out when you take one system out and bring another system in. You can easily swap that in and out. But that does have some capital cost up front, and those power taps, breakers, and the busways are all in high demand these days by the hyperscalers as well. So you tend to have to wait a while to get them.
So, like following on that, like I know the hyperscalers PU is generally like maybe 1.1 or even less. So that's kind of like aspirational for, I mean, I don't think it's even achievable in a small setting. So what kind of aspirational goals do you see folks who have smaller data centers looking at in terms of maybe just PUE?
Um, Well, we would like to get there. With Blue Waters, we weren't too far above that. As I mentioned, right now we're far from using all of our capacity, and that's part of the challenge for us, is that our capacities, our current usage is so low that it actually doesn't make efficient use of some of our infrastructure. So we have some new systems coming in that will hopefully increase that to the point where will make us more efficient. Right now, our PUE is not terribly good because there's not enough load compared to the size of the facility. So that's a piece that's a challenge. But yeah, I think when you get to on-site towers and things like that, as long as your capacity matches reasonably closely to your usage, you can be pretty efficient. It's In our current case, our towers are much larger capacity than we have load currently, so we can't effectively use them. So that hurts.
Yeah, I think just looking at the things you can control and making making these decisions for the things you can control with efficiency in mind. And if there is budget to do something with water instead of with air, you know, understand the trade-offs, and if it makes sense, jump into that. For us with efficiency, what we don't control the is the cooling down of the water that we send back on the facility side to the campus. And that is like the biggest cost. It is like a mile away. We're sending this hot water. They're cooling it down with uh, a bunch of these extremely massive cooling towers. But that is like the price and the metric that we have no control over. So that's just always going to be there as a baseline of we're just kind of beholden to whatever efficiency the campus plant can deliver, unless we can get them to build us more efficient localized infrastructure. And so I've just taken the approach of like do what we can where we make, when we're the decision makers, and then when working with researchers and PIs, oftentimes it just doesn't work out. They only have enough money for an RTX 6000 Pro or something, and it's never gonna go liquid cooled. But um, trying to have the conversations, trying to push maybe them into a shared environment. If we can build with our team a shared platform on top of a water-cooled environment that would provide the researcher a similar environment, similar experience at a similar cost. And maybe that's where we should be going. Um, and so, yeah.
Thank you.
Any comments from the audience on that? Okay, I don't know who put this question in for the audience question, but there's a question on the local environmental and ecological impacts in the sense of monitoring and reporting. I'm supposing that means around, have you folks, what kind of impacts have you seen with having to comply with local regulation of what goes on at the data center? It may be a loaded question for some. If you're uncomfortable answering that, I can understand, but anybody want to take a stab at that?
Or if I could rephrase a little bit, do you have any partners at your university that you're working with in
There you go.
ecology or environmental science that are looking at these things? I think that's something especially that our community is really interested in that could be nice partnerships and learning experiences as well as just helping us grapple with, you know, understanding our impacts.
We do partner with different parts of campus at different times. Sometimes those are just to help them understand that they're doing a research project and that sort of thing. There was uh, a design project that campus run around the time that our facility was designed that actually resulted in the addition of the on-site cooling towers. So that was an idea thrown out by that um, instructor in coursework. Suggested it would be a good idea and was tacked on to the plans at that point. Um, We've worked more recently with groups that are interested in, could geothermal play a role in cooling a facility like ours? And many of these ideas are very interesting to look at in a research perspective, and they could be made to work, but they take a fair bit of capital to implement. So, unless somebody can come up with the capital to do them, they're really not something we can justify putting the money into it. If we were building if we had back in our design phase, they would be something we could consider implementing because we didn't already have a solution. But when you've already got a solution, it's expensive it has to be a real big win to be able to justify the cost of swapping it out. But we are also, I mentioned the water um, use sort of questions that we're getting, and we're partnering with the Prairie Research Institute, which is our state-sponsored group that does water surveys around the state, and helping. In that context, we're mostly helping them understand how data centers use water and that sort of thing. Currently, our use is not big enough to really warrant much concern, and I don't think we have a lot of concerns here. When we built it, we didn't have a lot of concerns, but we partner, we talk a lot with sites that do. Certainly some of the European sites have had a whole lot more work to do to the cooling systems that they do. Like the Swiss in Lugano actually pull water out of the local lake and put it back in, and had to do a whole lot of environmental surveys to prove that wouldn't change the ecology of the lake because of the heat they're introducing. So, but they did it, and it works. Provides very low cost cooling for them. So,
Any other comments on that?
Any thoughts on recycling of equipment that you have been thinking about and life cycle management? Like, when do you really take things out?
well, I'll know Blue Waters. We actually operated for 9+ years of actual operation, and of course the thing that ended it was that no one was still interested in paying the power bill because it was a very power hungry system. Well, relative to its size, it maybe not, but it was a system that could pull easily 10 megawatts of power. So you had to have a big problem and need it running flat out all the time to make it effective. So we do run systems longer than the typical, usually grants are for like 5 years. And that's also typically what you get warranties for. So once you get past 5 years, you have to start thinking about how do you replace parts, or do you just have an attrition of, the system gets smaller as you can no longer fix something, or buy spare parts. So there's some of that, but our campus limits what we can do somewhat, because the equipment has to go through the campus surplus system generally, unless of course it's too big. Like Blue Waters was handled by a company that came in and specifically pulled it apart, and they did specifically recycle much of it, to offset the costs of the decommissioning. So we paid a little bit for that decommissioning, but not nearly as much as we would have if they were not able to recoup costs based on that. So they recovered metals, recycled metals. They took all the server blades and pulled memory and CPUs off of them to sell on the secondary market. Given that those were 10-year-old products at that point. I'm not sure exactly how much they got out of them, but that was the claim anyway, that they were able to recycle and reuse them.
Yeah, basically identical in San Diego with the campus surplus program, and then with their latest like 30 rack decommission, we brought in a third party to do that, and um, they sold components on the secondary market, I guess, and wrote us a small check at the end of it. And yeah, the only thing I'll say on the life cycle um, piece is one of the things I'm tracking is how these new pieces of equipment, these new CDUs behave towards the end of that decade that people want to run their traditional servers. Like, are these gaskets going to hold up, or are we going to get leaks in the facility? And right now we're dealing with an issue where the CDU is not under warranty. That people didn't really used to care maybe if their computer wasn't under warranty, because they can just get components off of a spare, or they can just send a infrastructure person down to swap out a drive. It's not a big deal. But when it comes to this like critical piece of what really is facility infrastructure, that's where as data center people we need to be more involved. And so I think there was like kind of this early approach of the CDU comes with the computer generally. And so is it operated as part of the people operating the computer, or is it operated by the facility? And I think that is another kind of partnership that we're figuring out, because we can't really have risk of leaks and risk of gasket failures towards the end of life for this type of infrastructure. Maybe this is like kind of overblown, but it's something that we're tracking, and specifically on this, like on these older cooling distribution units, we're getting like extended warranties on them, and you know
I'll tell you one thing I remember is, and I was going to ask this question is, how do you impose efficient data centers when your clients aren't paying the electric bill, but the university is? Because they'll run those systems forever if they don't have to replace them. And I saw your comment in the chat there, Scott, about the one that just got replaced after 10 years of service. I mean, that's another factor, is how do you explain to your users, hey, a system that is that old is clearly not efficient and not up to what is expectations of systems that are running the data centers today. So
It's even worse than that. The universities that were bidding to host those systems, where the awards were done in 2015, the systems went in 16, 17, and 18, were told they'd be running them for 5 years. and they ended up
Sure you
running
are.
them for 8.
Hmm.
Our,
So
Hi, I'm chiming in just before hopping to the next meeting, but our university actually has some policy around total lifespan of systems. And so at Tulane University, max life is 8 years or 2 years over warranty or so. And so it's kind of an interesting approach from, I think they looked at it from a risk management perspective. It only came into effect about 2 years ago, so I'm quite popular these days about transitioning for hardware, but it is an interesting way that they handled it. Thank you.
Hmm. I never heard of that. Brett or Brian, have you ever heard anything like that?
Um, so I'm not going to get this exactly right because I'm not directly involved with it, but our campus cluster program does have a policy on that sort of thing that their individual groups invest in nodes, and they do have a maximum lifetime in the cluster. Uh, Users can request their nodes out at the end, I guess, but that doesn't usually happen. But I think there is I don't know exactly what it is. I think it's more than 5 years probably, but I don't know exactly what the limit is. But they did impose a limit for the same reason that at some point things get so old that you just can't keep it up. And part of that's the node, and part of that's you don't want to keep, you're you're so many generations of InfiniBand behind or whatever that it's no longer easy to keep the networking and other equipment up, and you get fragmented. You have this old cruft on the side here, and you're trying to upgrade stuff, and it just makes it harder to keep stuff going.
Okay. Well, I think we're at time, folks, so I'd hate to cut up the conversation, but unfortunately we have to move on. Next month, April 5th, we'll have our spring meetings recap, same time. And thanks, everyone, and thank you to our panelists in particular for coming out. I appreciate it.